if you want to follow along with any of the examples in the lecture portion, just make sure you download the module 7 underscore data zip, unzip it to a place where you'll know what it is. It's the same data that we used in module 6. So if you already have that somewhere, you can go ahead and use that instead of the module 7 data. So we'll start by looking at a data type that I said early on in the course we'd get back into because it would be very important. And that's called the Python dictionary. So as we know, a regular dictionary is a container, like we see here. It's a book, and that contains keywords. And then after the keywords, some explanation about them. A Python dictionary is kind of the same organizational bit. So it's organized the way a regular dictionary is. In the Python, we have keys and then values that are assigned to the key. You can think of the value as the explanation of the key. So here, for example, in this dictionary, in the first item 1, I have coronavirus as the key and value as the disease COVID-19. Then I have another item that has a key and a value. The key is rhinovirus and value common cold. Although a coronavirus could also cause the common cold. This is just how it's organized here. So we have 2 items in this dictionary, and items are separated into key value pairs by the colon. The keys are strings. The values could be anything, any data type. And I just made them like a dictionary type of thing here, both strings or text values, just for illustrative purposes, but you could have a number in there as well. So the values can be any other Python data type. And then they're enclosed in the squiggly braces, the entire thing. Squiggly brace means dictionary in Python. And you assign the dictionary to a variable, like so. So Python dictionaries are structured quite straightforwardly, and they mimic kind of the structure of a regular dictionary, hence the name. Here we have another example. We have this small dic, so a small dictionary, and it has two items. The first one has a key called 1 and a value of 4, so an integer. And the second item has a key called 2 and another integer as the value. So it has 2 items and 2 key value pairs. We can check whether a particular key is in a dictionary using the in operator. So for example, 2 in small dic would return something, true or false, depending on whether it's in there or not. We can get a value by its key. So I can say small dic dot get, which is a method of a dictionary, and then the key, and that will return the value. So small dic dot get 1 will return the value 4. In this case, it's printing it out. We can multiply values of keys. Here's just an example of getting the value for key 1, getting the value for key 2, and multiplying them together. 4 times 5, which would be 20, and it's printed out. I'll make a small dictionary equal to open and close the curly braces. And then I give a string 1 colon, and I'll give that a value of 4 and 2 a value of 5. So that's now a dictionary. So I just run that, and then I look at it in the console at the bottom, and I just type the name of it. It will show me the contents of that dictionary. If I want to get a value, one of the two, I could get it by the key name. So I could say small dic dot get, then the key, let's say 2, and that will return, in this case, 5. because the key 2 has a value of 5. Or the other way around, small dick dot get 1. What if I did this? Small dick dot get, and I put 1 like that, what happens? Nothing. So just like case sensitivity in Python, strings are also case sensitive when they're keys within a dictionary. So 1 with a capital O and 1 with a small o are two different things. And notice I don't get an error here. I just don't have anything returned. The values could be worked with together. I could say, okay, what is small dick dot get 1 times small dick dot get 2, and it returns a value of 20, since I'm working directly with the values by getting the value from a particular key. If we want to just see all the values, I can just say small dick, and I'll put it up here actually, and I'll run it. Small dick, there we go, dot values. And I can print that. Or I'll assign it to a variable, I'll just call it X, like so. Then I'll run that line. But I want to see them, and values is a method. So I go like that. So Control F7. Now if I look what's in X, it says dict values for 5. So it omits the keys. We can add more key values by updating the dictionary using the update method. So if I want to add, let's say, a third key, so I could say small dick, or I'll make a dict first. I'll just say dict equals, and this is a small dictionary with 1 key value, 3 colon 6, like so. Now I have that dictionary. It's a small one, a very small one, just has 1 key value pair. And I'm going to update the current one. I'll say small dick dot update, and I want to update that with, it's a method, dict, like so. Now let's see what happens when we run that and check in on small dick. So Control F7 here. So nothing happens, and I'll just check on small dick now. You see here it has 1, 3, and 2. You'll notice that it didn't put 3 at the end. It just stuck it there this time in the middle. And that's because dictionaries are unstructured. There's no order to the dictionary and what might be in it. So certain processes in Python that utilize a dictionary may modify the order of things within the dictionary. And that's something important to remember. What if we want just a particular key value pairs to be returned from the dictionary? Let's say we want 2 and 3 to be returned. So we just want the values from 2 and 3. Well, we could do that in a loop. We would start by creating what's called a key list. So I'll just say key list equals, as a list object, 3 and 2, like so. Then what I can do is loop over. So loop over and get those values, just printing them out. For example, I'll say for val in key list, or I'll say for key, I'll just say for k in key list, since it's an iterable. Then I can say small dick, and I'll print it here. I'll make an X there, internal to the loop. X equals small dick, not X small dick dot get k, print X, since it's stored in there. Then I'll run that. And it prints out 6 and 5 in the console down here. 6 for 3, because that's a value belonging to key 3, and 5 for 2, its key value pair. I could do that instead in list comprehension form, which would be simply like this. I just say, I'll just call my output list X, and I'll just say in here, within a list, I'll say small dic.get K for K in key list. And if I run that, just that line there, Control F7. I don't know if it ran anything. Control F7. There we go. And then I look in X, it'll show me the key value pair. I should say the values for those keys in the list, and those values will be in a list like that instead. So it works well with dictionaries, work well with list comprehension as well. There is even dictionary comprehension, but we're not going to look at that in this course. So we see how easy a dictionary is to create and then to work with it and get the values. And I did these examples as well. So how to get all the values? You can just say dot values. You can get keys in the same way with dot keys. If you just want to see all the keys that are available, I'll just show that here in the command line. So I could say, what is it? Small dic dot keys, and it prints out the keys for that particular dictionary. And you can think of the keys again as the list of words, and each one of those will have a value associated with it. And often when looking at a dictionary, you want to look at the keys, because the keys allow you to then figure out which things you need to get by name from the dictionary. So the keys we can also do. We can update, and remember it's unordered. So when you update a dictionary, that key value pair could go anywhere within the dictionary. So dictionaries should never be, you should never write code that relies on dictionaries having keys which are structured or ordered in any way. And then the list comprehensions example there that we did. Now, these are really fundamental because something called JSON, JavaScript object notation, right here, Json strings, these are strings, are used as a common way to transfer data through hypertext transfer protocol and RESTful APIs on the internet. These are things for which your software or the site you're on to do something creates a URL, a very long, sometimes very long URLs that you'll see. And those are often containing variables and requests to a RESTful API, the most common type of API that is used today on the internet to retrieve or upload data. And Python dictionaries are structured just like JSON strings. So here, for example, what we see in this diagram at the top just says object, and that object means the whole thing that it's showing. And these lines just show the components of a JSON string. So we have open squiggly brace, closing squiggly brace, and that's just shown by that line there, meaning that everything else in the JSON string is connected or within the squiggly braces, just like a dictionary. And then within the squiggly braces, we have string, value pairs. And each of these, of course, is just like a item in a dictionary. And each item is separated by a comma. this format is the Python dictionary format and the JSON format simultaneously. And so what we see here could be a JSON string or a Python dictionary. And that means that when you use Python to make a request to a external application, not ArcGIS Pro, but I'm talking something like Google Maps or a geocoding application or something like that, or just an online database, well, you're working with Python dictionaries to prepare your data to be sent as a string to those types of services. And we'll be doing more with that next week. But you need to understand that a Python string and a Python dictionary are, for most, 99% of the time, exchangeable. There are some slight differences between a dictionary and a Python, or I should say a JSON string. And that usually has to do with the type of quotations around these things, single versus double. And there is a built-in library inside of ArcGIS, ArcPy, that can convert between a dictionary and a Python, or a dictionary and a JSON string. It's just called the JSON library. And it's like to JSON from JSON. Pretty much all you need to know. For example, we have the library called JSON. And we can just import it, import JSON, and we can take a dictionary and use the dumps method to convert a dictionary to a JSON string. Then to decode it back to a Python dictionary, we use the loads. Very, very simple. And another good thing is that with a dictionary, you'll see we can look at the visual structure of it hierarchically using many online JSON format tools. And we'll look at one here called the Json Editor Online. But first, let's look at the differences here. I'm just going to keep my small dic close by here. I'll remove the rest of this stuff since we just looked at it. And I'll say import JSON, like so. It's built in. Then we have our small dic dictionary, and I'll make a JSON string out of it. I'll just call it JSON string, like that, equals JSON.dumps. And then here, and notice there's a number of different parameters that can be allowed or not allowed. Sort keys, for example, by stuff like that. We're just going to use it straight up like this. So there are options here that, if you need to have a JSON string that has or conforms to a specific type of JSON format, look at these parameters and see, well, which ones are important for you to use. Here, I'm just going to put in small dic, like so. Then I'll run these just to show you. So let's have a look at our small dic. Looks like that, and then the JSON string. So what is the difference that you notice right now? Well, our small dic have single quotes. Even though we specified double quotes, it turned them into single quotes. Python did that. Then when we converted that to a JSON string, it converted them back to double quotes for the JSON string, and then put the entire JSON string in single quotes. But the inner part is identical. So there's, just to show you the equivalency between a string that is JSON and a dictionary. If I want to bring that back in, so loaded, I'll just call this loaded. Loaded JSON. That'll be JSON.loads. and that'll be JSON underscore string. And I'll run that as well. And let's have a look at it now. Loaded JSON. And it brings it back to a Python dictionary. So exporting to JSON a dictionary and loading a dictionary are very straightforward things. Now, for any dictionary, which is JSON, made into a JSON, we can go to a website like this one, Json Editor Online, and you can copy and paste your JSON string into here. They give an example here. So here's an example JSON string. Has the first value, or the first key, I should say, is named array, and then it has a list of numbers. The next one is Boolean, true, color, gold, null, null, number, 1, 2, 3, object. And then the object itself is another dictionary. And then it has another key called string hello world. And then we can look at that on the left, formatted like this. So it makes it easier to read the JSON string. And if I just copy it over to the right, like so, then it shows it in a structured hierarchical tree format. For example, array, that's this part here, which has a list of numbers. And then it shows us 1, 2, 3 like that. Object, which is another JSON object, looks like that. Key value, key value. This is just for visualization on the right, and is really helpful when you're making large JSON objects to store data in an online service or database, like a NoSQL database that accepts JSON JSON strings. Going back to PyScripter here, if I was to take our JSON string, it just has 1 and 2, and I can copy that and I can paste it on the left. Oh, and it says there's an error there. We get rid of that quotes, like so. So just the inner part, not the quotes in the string, and then I copy it over here, and it looks like that. Object 1, 4, 2, 5. So this is a good place to construct JSON or to construct complex dictionaries so that you can actually visualize the hierarchical format of what you're constructing. So you can stick your JSON string in there once you convert it to a JSON object, remove the outer quotes, and put it in a service like the Json Editor Online just to see the structure of it. Next, let's look at functions in Python. You have been using functions all the time in Python. Every time that you write a Python statement that has parentheses and you put arguments in those parentheses, you are using a function. Most of the time, those functions belong to a particular object, so they're called methods of the object. The functions themselves are carried around with the object as it exists once it's created. For example, when you get a layer from the mapping module, the layer has a number of methods in parentheses, method name parentheses, that you use to control or do things to the layer. So functions aren't new, but the creation of functions for yourself might be new. So let's look at this function in detail here. Functions start with a def statement. Def is just short for define. So define a function. This is a name you make. You make that up. So you make that name up, whatever you want to call your function. There's no rules except you don't call a function something that already exists as a method or function of Python. Then you specify any parameters that your function needs to work. You will assign arguments to those parameters. You might say that's equal to, 5, for example. So a parameter equals 5. 5 is the argument. And a parameter is the parameter. So when we assign the argument to the parameter, we evaluate it there. A parameter then is used inside the function body itself. That's getting a bit messy, so just erase some of this stuff. So we'll just say up here, a parameter, let's say that's going to be equal to 5. So a parameter is called a parameter, but it's also called a function variable. Because it's a variable that is used by that same particular name within the function. So for example, here inside the function body, I start with what's called a doc string, which explains how the function is used. And doc strings have triple quotes, triple quotes. So the doc strings are optional. You don't have to have them in your functions, particularly ones maybe that you're using on your own, or just ad hoc functions you're creating to make your code more efficient. But it's a good idea to have them so that it reminds you what that function and how it's used, what the parameters mean, etc. Because it will show up when you open up the first parentheses. The doc string shows up, that's kind of your little help file for that function. And then a parameter, again, is used by name here. And of course, if we said it was equal to 5 when we called the function, well, that's just the value 5. And here, multiplied by another 5, is stored in a variable. That's called a local function variable. That variable only exists when the function is called. Once the function returns something, that variable and its contents are erased, as is the parameter value itself. At the end of the function, we have those local variables. Then we return something using the return function of Python, and then in parentheses, whatever we want to return. In this case, we want to return a variable, which is 5 times whatever was set for the parameter. So we can have a look at how that works. Now, usually functions come right after imports. So if you're having functions that you're utilizing in your own script, the best place to put them is right after your imports. So for example, what do we call this one? A function. So I'll say def a function, and then in parentheses, a function variable, like so. And then I put a colon. Next, I write whatever I want in the doc string. So 3, and then I start writing this function multiplies 2 numbers. And those can be longer, so I could have a second line here where a function variable, and I can put a dash any number, like so. So I just write that doc string, and it tells us, it will tell us later what those things are. Then I hit my enter key, and I start writing the function body. So my output variable will be equal to a function variable times 5. And this doesn't do 2 numbers, it multiplies everything by 5. This function multiplies a function variable by 5. That's better. Then I return. I say return, open parentheses, output var, like so. So if I run this function, so I'm just going to run it, nothing happens. It just loads it into the Python session, so it can now be used. So I could use that, and I'll just go, I'm going to use it right in the console here. I'm going to say a function. Notice it even comes up when I type the word a function. And I want to put 99 in here and hit enter. 99 times 5 is 495. And notice how that works just like any other function that you would have, you know, like I might have a list, another type of thing. So I might say x equals a list of things, right? And there's all kinds of functions I could do on it. So I could say x dot, and these are all built-in functions for x. You know, I could extend it, index, you know. So value 5, and it says it's at position 2, 0, 1, 2. So that's a function that I just ran called a method because it belongs to an object. But I also have I could say length x. That's a built-in function as part of Python where I give it something that can have a length and it sends back the length, which is 5 in this case, because there are 5 items in x. So that one works just like our a function in terms of how it's called. Calling the function just means using it with a particular argument. So a function is a code block that begins with the keyword def, then the function name, and then parentheses for how many arguments you're going to have. You could have many. And if you have more than one, they must be separated by commas. Then the colon. Once you hit enter, you have an indented block whereby you define what the function does with its parameter variables or function variable up here. So we did something like a variable time equals 5 times the parameter. And then a return statement. The return statement doesn't have to be in parentheses, but you should have it in parentheses because return is in fact a function. It just doesn't need parentheses because it is used in a way consistent with Python 2.7, the older version of Python, where certain functions didn't require parentheses. For example, in the old Python, to print something, it was just print and then space and what you wanted printed. You didn't have to have parentheses. But we like to be consistent, and most languages, the return statement would have parentheses around it because it is a function. Also, remember the function body, as just again another reminder, does something with this variable here. That's a variable in the function body. So the parameter is a variable which is used in the function body. And that could store anything in it that is valid for the function. The doc string could be as short as long as you want. Then in return, I said, and if you have a return statement with nothing in the parentheses, nothing is returned. So let's look at the doc string a little bit more. So a doc string is a string literal that occurs as the first statement in a module, function, class, method definition. So doc strings are used across all kinds of Python language constructs. And for any function, class, module, etc., you can access the doc string by itself using the underscore doc special attribute. So my function dot double underscore doc double underscore can be accessed as such. So for example, back here, and I'll say a function dot double underscore doc double underscore, like so. And it shows this function multiplies a function variable by 5. So it just shows the doc string. The other way to get that is just help and then a function. Another help is a built-in Python function. And it says here, help on a function in module main, a function, this function multiplies a function variable by 5. So those are two ways to look at the doc string for any function or variable. Not variable, I should say, but any function or language construct. Calling a function, and that's obviously computer lingo. Calling a function just means using it. The function call is the line that specifies the function name and the attributes. So here, for example, is a function that takes an argument, just called arg here. It's called print fun, and it just prints something. So print squiggly braces dot format arg. So all it does is print the argument that's given in this case. So if I say print fun 10, it will just give me back the number 10. Going back here, I'll make another one. I'll say def print fun. And I'll just call that a var in here for a variable, or a param, better. And then here I have a doc string. This function just prints what is sent to it. Then I just say print whatever's in a param, like so. Now, if I run that function, so first I have to run it so that it is usable. Running the function itself is not the same as calling the function. Here, running the function is just like so. Control F7 to run that so that it's available in my console to be used as a bona fide function. So I'll say print fun, and I could put a dictionary in there if I wanted to. And all it does see is print whatever I sent it. Not a useful function necessarily, but it's a function nonetheless. And of course, we have functions where we do something with the argument. So in this case, for this example, this function returns a value. The last function up here didn't return a value. Notice it's just a print statement, not a return. So if we assign that function to a variable when we call it, we're not going to have anything in the variable. So if I did this, if I say, go back to that print function, I assign a variable, assign it to a variable, I'll just say x equals that. Oh no, didn't work. X equals this, then what's an x? Nothing, because there was nothing returned. You need to have that return statement for the calling statement to return some value and store it in a variable. So you can have functions that do not return anything and functions that return things. Some functions are just for printing out values or objects and stuff like that. They don't actually return a value that can be used for further computation. They're just for display, while others return values. Here's a larger function that doesn't return any values. Here, the function is called srefprint. So you might be wanting to make a report, let's say, of all of the information about a spatial references for a series of layers that you find within a workspace. And so you want to know what all the spatial references of each one are. Of course, you could open each one separately, double click on it, check the spatial reference, close it, open the next one, add it to ArcGIS Pro, double click on it, go to the spatial reference tab, and then the spatial reference properties, look at it, maybe write it down, etc. Very tedious, obviously, if you have more than one thing to look at even. So this function takes in a workspace and a feature class, and then gets the spatial reference for the feature class using a describe object, and then prints out important information about that, like the projection code, the name of the spatial reference, scale factor, standard parallel 1, standard parallel 2, and you could keep going, adding more things in there if you wanted to. So that could be a very useful function when you want to figure out which layers need to be, let's say, have a coordinate system change and which layers do not. And then calling the function is simply calling the function like that, and it then would print out all these things. Of course, you could have print, you could have, instead of print, write. You could open a file and write them all to a file if you wanted to. So there's all kinds of different ways you could have this function output things, but its requirements are now 2 parameters. So we have 2 parameters there instead of just 1. The first is a workspace, the second is a feature class. So for example, in the Ottawa geodatabase /data, I might want to go through there and look at the feature class neighborhoods. So we'll give that a try. So I'm going to just remove the stuff we have so far in here, and I'll start with importing ArcPy. And then from ArcPy, import env, import env. Next, I'll also import OS, like so, and that's to get a separator. os.sep is the separator for the particular operating system between folders, just as a useful thing to use. Then I'll set my workspace. So I'll say env.workspace, env workspace equals, and I'll just get it off my drive here. So I'll go to I have this here in my temp in a folder called module M7, module 7 data. Like so. I'll put an R quote, module 7 data, end quote. And then, data, and then Ottawa.gdb. And GDB. These aren't case sensitive, so it doesn't matter, but just keep it in the same case. So temp module 7 data, Ottawa, GDB, and then sub folder data. And I'll just have a list, make a list first. I just want to have see a quick list of what's in there. So I'll say, FC list equals ArcPy.list feature classes, like so. Then we'll have a look at that. So I'll just run that. Oh, I spelled ArcPy wrong up here. ArcPy. There we go. Run that again. There we go. And I'll just clear this console. So let's have a look at the names of each feature class. So I'll just do a quick list comprehension here. So I'll say print list comprehension, f.name for f in FC list, like so. And I'll just run that. List feature classes. Let's just look at FC list. Maybe I think it's just a list of names, if I recall. Yeah. Sometimes I forget that, this list feature classes just gives the list of names. So it's already a list of just names. I'll just make that a bit bigger here so you can see all the names. So we got truck routes, DAs, polys, et cetera, neighborhoods. And I want to look at neighborhoods to start with. So I'll say FC equals neighborhoods, like so. So now I have a feature class, I have a workspace. So I'll make a function now that will go through the neighborhood layer and list its components regarding the coordinate system. So I'll say def, I'll call it sref print, like so. And that'll take in the workspace and the feature class. Then I'll make a doc string. It'll say prints info about the feature class spatial reference. And here I'll put WS, a valid workspace containing FC. FC equals a valid feature class name. There we go. So there's our doc string. Next, I'll get a describe object or a spatial reference object. So let's say SR for spatial reference equals arcpy.describe, and then in parentheses, I need to specify what it's going to be, the describe. And here, I don't need to necessarily put the workspace or the full path or anything like that. Since I have set the workspace as Ottawa data, I could just put FC here like that. So describe FC, and I can say dot spatial reference. And then now I would do my print statements. Print SR dot name, print SR dot projection code, print SR dot scale factor, print SR dot standard parallel 1, print SR dot standard parallel, didn't spell that right, stand ARD parallel 2, etc. So now that I have that, I'll just run this. And it doesn't do anything, but now I can use that function either in my console or in my code up here. So I'll just say sref So before I do that, let's remove the workspace because we don't need that right now. There, it just takes one, this particular one, different from the slide a little bit, but this one here just takes the feature class. We don't need to say the workspace because we already set the workspace up here. But obviously, if you wanted to use this function in a different context, right, other than with this workspace, let's say in any particular, in a different script where you're not using one but many workspaces, then you would want to have the workspace in there like the example on the slide. So I just simplified it a bit here. That way you can specify which workspace is being talking about and which feature class is within that workspace that you want to describe, because you could have 10 workspaces, for example. In this case, it's just simplified a little bit. So I'll say sref, and notice here as I start to write it out, sref prints info about the feature class of spatial reference, ws a valid workspace, fc a valid feature class name. So it's just showing the little help in the doc string. So reminds you how to use it. Of course, I need to change that doc string here, take out the workspace, for example, since I only now have a feature class in there. There, and oh, didn't quite take yet because I haven't rerun it so far. So let me rerun it first so it takes the proper doc string. Now I can try it again. There we see now the doc string looks good up here. Print. And here, it'll just be the feature class. And there it goes, City of Ottawa 43006. The scale factor 9999, etc. Might want to add in here under name the projection name. Like so. So I'll just run it again and then I'll try it. That's better. So we have a City of Ottawa transverse Mercator 43006, and these are the key things. There is no standard parallel 1 and 2, so they're both set to 0 because it's a transverse Mercator here. It would have standard longitudes, about 1.5 degrees east and 1.5 degrees west. No, less than that. It's a 3-degree zone, so it's 1.5, so 0.75 degrees east and 0.75 degrees west of the central meridian of that zone. Then we could see, well, if we want to do it for a number of them in the workspace, we could just create down here code that loops over each feature class, right? I could say for FC in FC list, like so, colon, sref print FC. And that'll print out for every feature class all of the things. Now, since they're in a feature data set in a geodatabase, they'll all be the same in this case, but just to show you how it could be done. And then we can see it prints out for every single layer. And we might want to print the FC name itself to start with, or something like that. We can modify it. I'm going to print out here. Not those ones. Just separate it. Put a little separator in there. Print again. Here the FC name, feature class name. Then I can run it again. It makes it a little more organized to look at. So here we see, okay, well, they're all separated now, easier to read, neighborhoods, AOI, neighborhood dissolved, etc. And that's all done in the function. Now, you could, of course, modify a function like that to send back a list of all those parameters for each one. So it actually sends back something that is usable in a number of different contexts. But this is just to show a basic function. And our call to the function is very simple. And the doc string, we had to modify it because I did a little simplified one where I took out that part. But if you want to use this function generally, let's say anywhere, for any layer, then you'd want to keep the workspace in there so that the workspace is concatenated to with the OS separator. So that's going to be like on Windows, either a / or a a / or a double backslash plus the FC, which is the name of the feature class. So that this function is a little more general than the one I just made, which is tied to the workspace up here. Functions that return values, we have ones like this, which returns or the sum of a field. So the way to get the sum of a field in ArcGIS Pro, of course, is to right-click on the field, say statistics, and then look at the chart, and then in there it will show the sum. Now, if you have to do that for a bunch of different fields, that's tedious. So in this case here, this function, which is right there, that's the actual function itself. The rest of it is just stuff that would be in a regular script. So the function is called SumField, takes in a feature class and then a field name. Then inside of here, it imports NumPy locally just in the function. I could take that out of the function and put it up here, but then the function is less usable because you always have to remember wherever you bring that function that you have to import NumPy so that the function will work. And you may not have NumPy imported in all of your scripts. So you can import right in a script any of the libraries that would be needed to run something. So SumField is the name, feature class, and then a field name. For example, up here, a feature class neighborhoods, a field name, block pop 2011. Then it converts the feature class table to a NumPy array, because feature class tables to NumPy array is quick. And then NumPy arrays have a sum method when you specify the field. So that's the quickest way of doing something like that, the most efficient. The other way would, of course, be opening a search cursor and then iterating over each of the records for a particular field, summing them, and then outputting the final sum value. And that would be slower overall than this way. So this is a more efficient way to do this type of thing. So let's give it a try. I'll just grab a new module for that. So I'll import ArcPy again from ArcPy import env. And then I'll set my workspace the same as before. So I'm just gonna actually go back and copy that workspace so I don't feel like doing it all again. Like so. So there's our workspace. And the feature class be neighborhoods. And the field that I'm interested in for summing is the one called BLK pop 2011 to 2011. My function, def, sum field, and that'll take in the feature class and the field name. Let's call it F name there, or FLD name, like so. Forgot my colon. Next, I'm going to do my import, local import for the function NumPy, since I'm going to be using functions and methods of a NumPy array. Then I convert. So I'll say x equals arcpy.da.table to NumPy array. And this will be again here. Oops. Feature class, and then the field name, close parentheses. So that gives me an array with nothing in it but one field. And then I can total, I'll just put total here, and I'll say that's equal to x dot sum, and then in parentheses, or actually x, then the field name, since that's what it's called, that column, the field name dot sum, and then I'll return the total. so. And there I have a function now that will take any feature class and field name and give back a sum of a particular field that you specify. And this could be used in any other script because it's not dependent on that workspace exclusively. So as long as you specify a feature class or a full path to a feature class, you can use this function. Then I can call the function down here. I could say, okay, print, I'll call it and store it. Total sum equals sum field, feature class field, like so. Then I'll print that out. Print total sum, like so. And I'll just get a bit of room here so we can see it run down there. I'll just clear the console. And I'll run. Oh, spelled arcpy wrong again. Arcpy. Then I'll run. And there's the total for that field. 877,318. So that's a function that returns values. Now, when we have a number of functions that we find useful, that we would want, let's say, want to use in different circumstances or in different scripts, well, one way, of course, is to always just copy the functions you want and paste them after your imports in your new script. But that can be cumbersome, and you're prone to having to go to many of your other scripts to find those functions. So whenever you create a function that you find useful and that you think you might use in other scripts, then create your own module of functions. And it's really easy to make a module. You start with an empty script in PyScripter, for example, and you keep all that default code in there because those things are necessary for a module. Then you put your imports right after the opening parts of the comments, where you can change the name of the module. You can give the module a name at the top, who is it by, when it was created, etc. What the license is. You can fill all those in as you see fit. Obviously, you can leave them all default values if you're just creating a module for your own functions. This doesn't do anything. It's just for the module information. Then we put our imports, and after the imports, we just have our functions. Well, I should say not our functions. After the imports, and then after the two default things that are in there, we then put our functions, like the two we just made, for example, sref, print, and sum field. The first default thing in there, def main, is where you would put code that could run by itself if the module was run as a Python script, which we're not interested in doing right now. Then the part that says if _name equals main, that just goes back to the main. And again, that's if you're running this as a .py file, let's say from the command line, then it would go back to the main and run the functions here. By default, we just have pass in here, which means this is not something that runs by itself as a standalone module or script. So pass just means skip that, don't do anything. It's just gonna not do anything by itself, basically. That's kind of all you need to know about those right now. Again, those just usually contain default code that can be run to test the module's functions, that they're working correctly, for example. And you'll see that frequently in more official modules that people release. They'll have code in there that can be run that for which the answers are already known, so that you know that it's working the way it should. Why? Because people often will get a module of functions. They'll modify functions, but they want to make sure that everything still works properly the way it should. And so they can always run those function calls that are within the main to verify that it still works after modifications the way it's supposed to. I'm going to make a new thing, and I'm going to keep all the default stuff in there for the first time. So for the first time, we won't delete everything in there. And again, up here, you can change things. I'm going to call this, my personal module. Author, I can put there, I can put license down here. GPL version 2, whatever, doesn't matter. The date's already there, so that's good. Then I start my import. So I'm going to import ArcPy, obviously, because that's important. And I'll say from ArcPy, import env. Then I skip. I can leave a bit of space there. I skip these two things, and I start to put my functions down here. And I'm just going to go and grab and copy and paste them. So the last one was sum field. So I'll copy that one, and I'll paste it. And the order doesn't matter where you put them in here. So now that's a module function. Then I'll get the other one for the spatial reference to print the spatial reference stuff. So I'll grab that, copy. Oops. And paste over here. Like so. So now I have a module, and you can keep adding to that as many functions as you want. So I could even have that and then just return. So there's just you don't have to put this. I'm just showing that you can have many functions in here. Then you want to save it, and save it to a place where you would save generally all your functions or your stuff where you know it is. You need to know the path to where you save it. I'm just going to save this to ctemp. So I'm going to say save. And then where should I put this? Ctemp, I said, right? Yeah. I'm just doing it because I don't care about it. So I know I can delete it later in there. Now I give the module a name. So I'll call it my functions, such as that.py. This name is important because it is the name that you will use when you import that module into your other script. In other words, the name my_functions is what you would import without the .py extension. So I know it's in ctemp and it's called myfunctions.py. Now I can close it. So we'll go back here to the previous example, which was the sum field one. And I'm just going to remove the sum field function from there altogether. The old function is in the Python interpreter still. So I'll just close that interpreter, reinitialize the interpreter. So I'll go to run Python engine, reinitialize Python engine. There we go. Now if I run this, it's importing ArcPy, so it takes a bit of time the first time. Then I get an error. So it says traceback, most recent call, name error, name, sum field is not defined. So it's saying that this function is not defined, and it's not. There's no function in here that this interpreter knows about called sum field. So that means we have to specify or import our functions. So if you recall, I put mine in ctemp, and there's my functions.py. So what I need to do is import that particular file, that Python file or path, into my current Python session, like this. So to access your custom modules, you just have to append the path that contains your custom modules to the system Python path using statements like this. So I import sys. These are system functions, and eventually, if you go on in Python, you'll see a lot about these things. Sys is used very frequently. Sorry. Then I say sys path append, and the path to my module. And then I can import my functions like so. Or I can say from my functions, import a particular thing. So going back here, up at our imports, we need to go this. We have to say, okay, import sys. And then we say sys.path.append. And then I want to get the path. So I'll just say C temp, easy enough. The interpreter doesn't yet know about these things. I'll just run those two lines, control F7 like so. So now I can say import from my functions, import some field. And there we go. Now it works. There we see our values. And maybe also I want to, have down here a printout of the spatial reference. So I'll say, instead of some field, I'll say import all, like that. Then down here I can say, what was that called? It was called sref print. And we just need a FC in there. Now I'll run it again. And see, it uses the sref print function and the sum field function without having to have the functions inside this particular script. So I'll just make that a bit bigger so you can see it. So there's the sum of the field and then the neighborhood's spatial reference information. So those functions are now available in this script by virtue of these two simple statements. So syspath append is temporary. So it temporarily adds ctemp where my functions file is to the Python path. And then I can import either specific functions or all the functions in there, like we've done here, and then use them. So I use some field and I use the sref print function. So again, that's why it's important to know where your module is of functions that you use frequently. And then just keep adding functions there as you create them so that you could use them in other scripts all the time. As you get more experience, you might find, for example, that a whole bunch of the functions have to do with layers, things you're doing with layers, for example. So you might create a separate module just for layers. And you might find that a whole bunch of functions in there have to do just with rasters. So you might make a rasters module. And that's kind of how ArcPy, you could think of that's the way ArcPy with all of its modules is created, as a mapping module, MP module, spatial analyst module. And these are modules that relate to each other thematically in some way to operate on similar data types. And so you can make many modules as well. And if you have enough, you could put them into a package. But we're not going to talk about this, and you can read about packages on the internet. I stored my functions like that in, well, here I'm giving C data. I use C temp in my example I just did, same difference. So importing, we imported sys, we appended the path to where our module was. And here's another example of imports. I import my functions as M. So instead of importing everything from my functions, I imported them as M, so I have to precede M by the name of the function. And that's just a safer way to do it, because then you're not, you're guaranteed not to overwrite other functions by the same name. So that's a safer way to do it. Here I imported env, set a workspace, feature class neighborhoods. And then I say here, M, for example, dot sum field, and then I give the correct arguments to get the total for that field, block pop. And so you see there's no function in here that's spelled out because that's in the module, and I just imported it. And then said M dot sum field is one of the functions that's in there. So it's like a method almost of that particular module. Next, we have what are called classes. Classes are the quintessential things that we often refer to as objects. But classes are just basically like a form. Think of a form that you fill out. Before you fill out the form is just a bunch of questions without answers. Once you've filled out the form, whatever that form might be a questionnaire, it might be a application for a job, it might be an opinion on something or an evaluation of something, but they're just forms, right? They're blueprints or templates for things until you fill them out and complete the form. And by analogy, a completed form would be called an object or an instance of something that that form refers to in the real world, so to speak. Classes are much like that. Classes are like the form itself, whereas objects are a filled out form. So to create a class is to create basically a blueprint or structure for filling in data and also filling in things that can operate on that data called methods. So let's start at a simple class here. Classes start with the keyword class. For example, here we see class, then tree. Tree is the name of the class, and inside, object. Classes in Python inherit from what we call object. Objects give the classes certain properties and methods, particularly the private ones that you've seen, things like double underscore, something double underscore. These are inherited from objects and automatically become part of the class for any object in Python. And we declare the class just like it would be a function and use the class keyword instead of def. And only one single parameter for a class, which is called object. That object could be another class altogether, which object itself is. Then we have what's called the initialization function. And this is the function that is used to specify the data that is stored within a class instance. So the things you would fill in to make the form particular to something in, let's say, the real world or something you've observed, etc. So the initialization class or init function specifies the data that the class will use. In this example here, we have 3 parameters to the initialization statement. The minimum parameter you must have is self to have a class. Self just refers to the class instance itself. Then we have other ones that you specify for whatever particular class you're creating. Here we're creating a class called tree to represent or hold information about a specific tree location. And so we have X and Y as the class variables or parameters. Then 2 internal object variables called self.x and self.y. This makes the X and Y's available to any functions that are defined within the class down here, like def this, def that, def that. We can always ask for the values by saying self.x and self.y in any function within the class itself. So these are kind of like a function's parameters, but here they're called the attributes of a class. Instantiating a class means that once we have a class defined, then we can use it to create instances of that class, as many as we want. So here, for example, tree is the name of the class, and we know it takes in an X and a Y. Self, again, is internal to the class. So that self argument or self parameter is not used outside of the class. So for example, to make an instance of the class, we store it in a tree and we say tree 9, 8. 9 is X and 8 is Y. Then, once we've done that, we can query the attributes, such as saying, what is atree.x and atree.y? So we've given values to X and Y in the class, and we can query them by simply asking about them using the class instance name and then dot parameter. And I'm going to make a brand new file like so. And in here, I'm just going to remove everything and I'll just type class tree and then object like so, and then colon. Then I can put a doc string for this class, just like you would for a function. Class represents a single tree. X, or I could say class attributes. X coordinate of the tree, Y coordinate of the tree, like so. So that's just my doc string. Then I have to have my init function. So def __ init __ self, and then the attribute X and Y, colon. Now I assign X and Y, which are user defined when you create an instance of the class, to internal class attributes using the self.x equals X and self.y equals Y. And that makes these available for any other functions that I'll write in here, and we'll do some more in a second, and also makes them queryable. So I can run that class. Nothing happens when you run a class. But down here, I can then make an instance of it. I could say first tree equals tree. And notice how it has a little different symbol. It's a class, and it shows the doc string. This class represents a single tree. Class attributes X coordinate, Y coordinate, tree. And then I could put X comma, not X comma Y, but actual values like 2 comma or 45, 44 comma 67, like so. Now, when I run that first tree, and I'll look in the, I'll just do it in the console down here to show you what it looks like. So if I just type first tree like that, it just says something main tree object at. And you've seen things that look like this before for objects, such as when a list function returns objects. This is how an object looks like. So if I want to query anything about that, I could say first tree dot X, enter, and that's 44. First tree dot Y, 65. Not only that, I can modify them. These are read-write by default. So class attributes by default are read and write. All I have to do is say first tree dot X equals 0. Now, if I look at first tree dot X, it will be 0. See, I've modified the class attribute for X. So when we created the first tree up here, right there, we made an instance of a tree. And that tree, that first tree variable, is an object with attributes X, Y. And other attributes, I could say help, first tree. And it says here, this class represents a single tree X and Y. Methods defined here are init, dict, if defined, and for example, weak ref. So it gives us information about that class. Or I could say first tree dot double underscore dict, and it returns the X and Y values as a dictionary. You're probably wondering, how did it do that, since the only thing I have in here is the initialization function? Well, these other functions come from object. Object is a generic thing that basically provides a whole bunch of methods to any object you create in, or any class that you create in Python. You could kind of think of it again, if you use that form analogy, that there's a basic form, right? That it would have like at the top name, student number, date, and those would be on the top of any form that's created at the University of Ottawa. So every form that's created would automatically have the fields put in there for date, name, student number, and then you would put in your own particular attributes or just questions that you want attributes for to be collected in the init statement here. So that's a good one, dict. And often we would just have a thing in here that says def, like this, dict, or def dict, self, and then just return like so. Now I can say first tree dot dict, and it returns the dictionary. So that gives me, because dict again is a hidden method, it's there. To make it unhidden, I give it a explicit function inside the class, or in this case, function is called the class method dict, to give back a dictionary of the attributes for the class. You can call that toDict up here if you wanted to, or whatnot. And that's the basic practice. You don't want to rely on hidden methods, but you can use hidden methods within the class itself as a shortcut. So we instantiated a class like we did here, and then we could look at the attributes. Instantiating means making an instance, and that instance is different from every other instance of a tree. I could make multiple trees, and none of the tree instances talk to each other. And everyone would have its own unique X and Y, which are class parameters. For example, here I make one tree called a tree, and then another tree, and I just call it another tree. Both have different attributes. Both are separate things and have their own space in memory in the computer. And then I could say print the first one, print the second one, its attributes. So once it's declared, you have an instance, and you can have many instances, or you could have one instance and you can change the parameters of it, or of any of the instances that do exist. But you can't do anything about changing the class itself unless you go and change the class code. Instantiating multiple classes just means assigning multiple instances to multiple variables. And then each variable, which represents an instance of the class, has its own attributes. So here's the example of adding some more attributes to our particular data structure. Now, generally, what happens here? So you understand why I'm showing you this next thing. I'll just run it like this. And what I get when I run that, without specifying values or arguments for the class attributes or parameters X and Y, I get this error. Init missing 2 required positional arguments X and Y. In other words, I can't just create a tree instance like this and then fill it in later. So in other words, fill in the values for the internal variables later on. What I have to do in that case to be able to do something like that is I must give default arguments to each of the inputs, except for self. So I can say X equals none, none, and Y equals none. Now when I run this, it will be okay. Now, first tree, if I just look at it and I say .dict, just gives me that. And if I, it's a method, so I put the open and close parentheses, and it gives X is none and Y is none. So having default values allows you to instantiate a instance of the class. In other words, create a tree object in code without specifying the parameters at the same time. Now, with that first tree, I can say first tree dot X equals 10, first tree dot Y equals 89. And now if I look at the first tree dictionary, it's filled in. And you'll also notice here how it's a little bit different from assigning regular variables. Because in the case of, well, it's kind of the same in that we're saying this store in first tree Y 89, first tree X 10. So it's kind of similar to regular variables. But what it does here is it maintains those changes in the memory that first tree is held within. So we could add some other types of things to this. For example, species and height. So we can add additional things. I could say self.species. And also equal something, and self.height equals something. Then I can just specify them up here. So I have to say species equals none and height equals none. It gives me the ability to instantiate a tree without any arguments. So species will equal species and height will equal height, like so. So now if I want to make an instance of this one, again, I just added 2 new attributes to the class. I can say the following. I could say, X equals tree, and then I could fill them in all at once. I could say 10 for pine 15, like so. And then x.dict just to look at the values. Oops, method, like so. So now the height is 15, species is pine, X is 10, Y is 4. Or I could have just said X equals tree, like so, an empty instance. It's now an object X, which I could fill things in as I want to. So if I just look at the dict first, there's nothing in there, right? Everything is none. So I could say, okay, X dot height equals 21, X dot, not X, yeah, X dot species equals spruce, X dot X equals 2, X dot Y equals 4. Now, if I look at the dictionary, it's all full of values. So we added a couple more values, species and height. And we looked at the values using dictionary, which is fine. Or we could have printed them out manually like that. Print h3x, comma h3y, comma this, comma that. But that by itself is cumbersome if you just want a nice pretty printout of all of the attributes. So we can add another method to our class, like values, for example. So if we look at our class right now in X dot underscore underscore, there's nothing for values. So there's no way to get attributes except for the get attribute. And then we have to give the name like species. And then it would give us that way. So it does have a built-in function or method that inherits from object called get attribute by name, spruce. But we might want to have a nice way to print those out instead. So we might have a values method that just takes self, the object itself in, and then prints out nicely species, X, Y, height, like that. So going back in our class here, I'll say def values self colon, and then I hear how I want to print it. So I want to say print, keeps putting extra ones there, print, in quotes, squiggly brace, colon, space, dot format, self dot species. And I'll just copy that and change it for the other ones. So I want to print out 4 values. Of course, they've got to be indented underneath the method. So print this. One of these I want to be X, Y. So I'll print X, comma, Y here, like so. There won't be a colon in that one. And here I'll say X, comma, Y equals that, just to show it in a set type of format. Dot format. So we have species, we'll put height here for the second one. That's the attribute we want. And we won't need this third one because we only have 4 attributes. We're putting X and Y in the single one here. So that'll be self dot X, comma, self dot Y. And we can run that. So now we have a class. I'll just make that a bit smaller, just so you can kind of see the class as it is right now. I don't want that in there, just the class. And I'll clear the interpreter down here. So tree is an object. We have an initialization, it creates the object and its attributes. We can then ask for values or a dictionary. So I'll make another tree. I'll just call it a tree equals tree. and I'll assign them while making the tree. So I'll say, you know, that for Y, species, maple, comma, height, 20 meters, like so. So I want to see a nice printout of that. I say a tree dot values. Don't have to send any arguments. And it prints out maple 20. Oh, I wanted to have this another way around. My printout, I can go quickly change it here to the species. Comma, squiggly brace like that. And height. Like so. Now I'll just rerun that. And I'll just go up, rerun that. Then I'll do a printout. That's better. So now we see species equals maple, height is 20, and then the XY is 345.23. So both of the functions that we put in there are now called methods. One is values, one is dict. What else could we do? So our methods just print out stuff right now. We could do other things like as list. So we could have another function in there that would convert our particular data set to a list instead, which could be useful in circumstances like if you're doing some sort of analysis and you want to loop over a bunch of trees and you want an iterable, well, getting a list would be good. So we can add that in. First, we always check to see if that is available already as a hidden method. So I'll say a tree dot, and I'll see if we have anything. We have class, delete attribute, dictionary, dir, doc, ec, format, get attribute, greater than equal. Not that it's useful in this case. Less than equal, module, new, reproduce, split, set attribute, size of, string. There's no thing here that's list or to list. So it's not there. So I'll make it. So I'll say def to list self colon, and then return a list. And in the list will simply be self. I'll do it in this order: self.x, self.y, self.species. No, let's put the quantitative ones first. Self.height and self.species in that order. And maybe we need a doc string to explain the order. So I'll put a doc string in here. So it returns a list with order X, Y, height, species, like so. Then I can run that. So I'll just check my tree right now. I'll need to create the tree again. So I'll go back up till we find the tree rather than rewriting it, hitting my up arrow. Oh, I don't know where that went there. So I'll just remake my tree. So I'll clear this. So now that I have my new toList method, I'll create a tree. I'll say, okay, here we go. A tree equals tree. X2, Y4, species, maple, height 20. There we go. And to have a nice printout, I'll say, or to get a list, I'll say TList as a variable equals a tree dot to list, like so. Then TList has a list of values. We could get the dictionary, a tree dot dict dot dict method like so as well, using the built-in private dict function. We could have had our own dictionary function as well. We could make it from scratch, but we already have one. And as I note here, but this is an example, def as dict self return, and then we just return a structured list like so. So this is what we look at more or less so far. We have our tree data structure, and then we have our methods. And we have 3 or 4 methods so far. Now we could do some other methods, things that do computations. For example, using distance 2. So how far is our tree from another set of coordinates? So it's a function that computes Euclidean distance, where we'll have a px and a py, which are the coordinates to which we want to measure distance. And then we use Pythagorean's theorem right here. And notice we import math, then we use math square root here, and then the square root of x minus the other x squared plus y minus the other y squared. And that returns us, in whatever our map units are, the distance. So that's a computational method. So going back to our class, we'll have a distance 2. So I'll just say def distance 2, distance 2, of course. And notice I'm using camel case for my methods to be consistent with Python methods on objects. Camel case meaning, of course, that we start with a small or minuscule value here, and then we go and we say our next word would be a majuscule or uppercase. Distance 2, self, comma, and I'll say px equals 0 by default, and py equals 0 by default. I put those in there just in case somebody calls it without specifying them. It won't give an error. It'll just find the distance to the Cartesian origin. Then I import math, since I'll need it for this function. I need it for this method, but not everything else. Finally, I create my distance equals math.sqrt, parentheses. And then I'm going to have things in here, which is going to be x minus x squared. So squared plus y minus y squared. Like so. Then I fix those in here. So I'll have self dot x minus px and self dot y minus py, like so. And then I want to return that. Return distance, like so. So I'll now run my class. And I'll go back and I'll just take that first a tree like so. So if I now say a tree dot distance 2, the method like this, it'll find it from 2, x equals 2, y equals 4 back to the origin, like so. Or I get a distance 2, some other x and y coordinate, and it gives back the distance to that. So it's a computational method, which is basically just a function to compute distance within the class. We could also have this class compatible with ArcPy. So for example, we can create a point geometry. So we can have a 2-point right here. In order to create a tree as a point geometry to use with other, let's say, geometries in ArcGIS Pro. So we create a geopoint, and I'll change that to geopoint like so, or no, geopoint's one word, so to geopoint. And then I have here self, and then a spatial reference as none for the default. Because you may want to specify a spatial reference that belongs to the point geometry. Because remember, point geometries have spatial references, like any geometry type in ArcGIS Pro. And if we want to use the point geometry with a ArcGIS method for other things on different objects or geometries, it must have a spatial reference with it. But we'll just leave it on null for now, or none. So going back here, I can say def to geopoint. You put geopoint like that, or geopoint. I think it's better like that. To geopoint. Then we have self and spatial ref. And we'll set that equal to none as a default. And then I'm going to create a point object first, but first I have to import ArcPy. So I'll say import ArcPy. Next, I'll say ArcPy, or I'll say, I should say PT equals ArcPy dot point. And this will be self dot X, self dot Y. And then GP PT equals ArcPy dot geo point. I think it's geopoint like that. Let's just check again. Point geometry, sorry. ArcPy dot point geometry. And then in here, our point PT, and then the spatial ref. Like so, and then return GPT. I think we should call this 2-point geom. Makes more sense. Or to ArcPy point geom. So at the end, then we have a ArcPy point geometry being given back. So I'll just run that to update the class. Then I'll say, okay, there's my tree. So I want a tree dot to ArcPy point geom. And I won't put anything on there just to show you. I spelled ArcPy wrong in there. Again, ArcPy. There we go. Update the class by running it. Go back, make a new tree, and then 2-point geom. And because it has to load ArcPy, it can be a bit slow the first time. And then we get that. And I should assign that somewhere. I'll just call it PT. Like so. It's fast the second, third time because ArcPy is now loaded, of course. So then I have PT and then dot all of the different methods that belong to a point geometry from ArcPy, like angle and distance to another geometry. So let's say I wanted to have 2 of these, right? So I'll make another tree. I'll have this at location 22, 54. It'll be a pine tree. It can have the same height. And I have a tree and a second tree. So I'll call it PT2 equals a second tree dot to ArcPy geom, like so. Now I could say PT dot angle and distance to And then in here, the other geometry, PT2. And it gave me an exception here. Didn't like that. So creating the geopoint then means you have a point that you could then use with other geometries. And if you give a spatial reference to it, you could then utilize the ArcGIS ArcPy methods to do other computations with point geometries based on your tree coordinates. So this is kind of what our class looks like now. We have 5 or 6 methods in there. To save the class, we do the same thing that we did with our module. We save it to a place where we know it is, so we can import it. So here, for example, I'll go back and I'll say, okay, here's my class. I'll say File, Save As, and I'll put it, I'm just going to put this in my temp. Maybe I already saved it there. Check it out. There's our tree class again. So it's in our temp. So I'll say File. I'll just make a new file to try it out. Delete this stuff. And I'll say first, import sys, import sys, and then I'll say sys dot path dot append and c temp, like so. Run that. Then I can say from trees, from tree, import tree, like so. So now that I've just cleared my Python window below, just the console to make it clear. So I import sys, and then I append temp to it. And then from trees, so that's the file. Oh, and temp, that's a different one. Yeah, there it is right there. Temp trees.py. I say from that file, trees, and I don't use the file extension or anything, just from trees or no quotes, import the class called tree. Then I can say tree, or I can put in a variable here, a tree equals tree dot tree, and then I can say, 4, 3, pine, and let's say 9 meters. There we go. So we now have a tree. So if I run that, run it, there we go. We have a tree. So I could query it, a tree dot values, and it looks like that. Species pine, height 8, x, y equals 4, 2. So now I'm using my class in a separate script altogether. My class is not loaded inside of PyScripter. It's just simply now sitting on the disk in ctemp. And if I need to modify the class, I would have to reopen it here like such. Then I could add more methods to it and whatnot, save it and close it, and then reload it. Now, one thing to keep in mind when you're doing this is sometimes you will start having problems if you're running this script many times. Sometimes you have many problems with sometimes loading things from that folder. And it's because what happens is every time you run sys path append, it appends another instance of ctemp to the search path for Python. And you can check that here, for example. Here I ran it a couple of times. So if I say down here sys.path, just to have a look at the paths, at the end I see a couple temps there. The only way to get rid of those, or the quickest way, is to close and reopen PyScripter. Then it resets everything back to the default path and run it. Or make sure that you, after you run it once, do that and do that, so it's not running a million times. and adding to the temps down here. Sometimes it gets very far, gets a lot of them. You can remove, so I could say, okay, well, sys.path.remove, and I can say, okay, remove an instance of ctemp, that, and then sys.path, and see there's only one left. So you could do that as well. So if you start having problems importing, it's probably because there's too many instances of syspath or syspath in a different way. So there might be a, you might have had that, for example, in one case. And then another different type of ctemp or something. So it's best to just do that once and not keep running those lines. Now, the way you could check it, right? You could say, okay, before I actually append to the path, I could say, okay, if ctemp in sys.path or ctemp not in sys.path, then do that. So if I run that, I'm just going to run it like a few times here to show you that, okay, well, now let's look at syspaths. And it still only has that one instance of ctemp in there. If I remove that instance, then it will run and append to syspath. So if I say sys, or I should say sys.path.remove an instance of ctemp, and I look at sys.path, see it's not there. Now if I run this time, it'll be there. So I'll say sys.path like so in the console, and there's ctemp. If I run it again, and then I look at syspath, there won't be an extra ctemp there. So I could run this like 10, 15, 20 times, and it's not appending another ctemp every time. Still just the one. So be careful when you're appending to the system path, because you may have done it in a number of different ways and they all just accumulate. So it's better to do it like that when you're using custom modules and custom classes. So importing is pretty straightforward. And then we can use our class. In this case, I imported, I had a different file name in the example here. I had a small trees as tree, and then I used tree.tree, etc. It works fine. Now, the last thing that we'll look at regarding classes is inheritance. Sometimes you want to modify a method in a class without changing the original class or rebuilding the entire class and calling it a new name, for example, trees2. So for example, in our class right now, we have a asDict method that uses the built-in inherited thing from object, which is $_dict$. Let's say that we wanted to have a different type of printed dictionary, one that's always printed in the same form put in. So we might want to have this instead, so that it has species dash as the name, because right now it just prints out X value, Y value, species value. So we want to have some different names going in there, let's say like this. Well, we could just go in and change the class, but that's not recommended. Instead, what we do is we create another class that inherits from this class. So all the methods and properties that this class have automatically will be on the new class. And then we overwrite a particular method with the one we want to change. So for example, if this was our original asDict in the class as it is, we then rewrite just that method in our overwriting class, or our new class, which overwrites doesn't overwrite, but changes that particular method through what is called inheritance. And it's very simple. We have tree. So we have a tree class, and then we make a new class called new tree. And it inherits from tree.tree. And this form will depend on the name of your file, obviously, here, .tree. And then we have to override a specific method. We just put the new method in. And then for new tree, all the other methods are the same, like values and geopoint and everything. But as dict will output something slightly different, like we see right here. And that's one of the advantage of object-based programming, is this idea of inheritance. If there's an object that you like the behavior of, except for one little thing, well, you just inherit from the object, create a new one, and overwrite that one method in your new object. And then it behaves the way you want it to. So it's kind of a customized tree version. So going back to the code that we have, so we have imported trees. From trees, we imported tree, so we have the tree object available. And to create a new object that inherits from that, I'll just call this this new one class new tree. So, and that class will inherit from tree instead of object, because it really does always come from object anyway, because anything in tree, which tree inherits from object, will now be inherited by new tree. Then all we have to do is specify either a new method we want to add or change an existing method that we want to have behave differently. Let's add a new one just as an example. So I'll say def print all self, like so. And here I'll just say print self dot values and print self dot dict, like so. And print anything else we want to print out here, self dot to list. So our new method, which inherits from, well, our new method is new. All the old methods inherit from tree. And the new method is called print all, and it just prints all these sequentially. So we can see all those different forms of information if we want to. So I'll just run that, and it creates a new tree instance. So not tree, but we want this to be new tree, like so. So I'll run that, makes a new tree instance, and a tree now dot has everything that the old tree had, plus this one here called print all, which tree doesn't have. So I say a tree print all, and it just prints all that stuff out. Oh, toList is of course, it's a method, so I'll just rerun that and print all method. There we go. So we see it here then, all the values as a list. Dictionary, printout of the attributes. So that's how you can add to any object that you like, just by modifying it to do a particular thing differently. It's very easy. And this is called extensibility. So the objects or the classes are very extensible by doing these things yourself. So to start a new or class based on another class, we call the class by a new name, and then we say what it inherits from, what object. In our case, it was tree. Then in the slide example, we overwrite an existing method to do it slightly differently, like the dictionary method. We then can make instances of the new object and call the new method, as well as any of the other old methods for the original tree object that the new tree inherited from. So in summary, classes are just defined code blocks, and they are used and imported kind of the same way as functions are. And the class describes the code and defines how an instance of that class is going to work, or what it will contain, or what it must contain. Classes are data structures. Some classes just hold data in a structured way and have methods just to, convert that data to different types. And in this way, classes encapsulate both data and functions that work with that data, called methods, inside the class definition. And they can be complex data structures and methods, and some classes are very complex. A variable that's inside of a class is called an attribute or property. So that's just the terminology for variables inside of classes. A function is called a method inside of a class. It's a function that does something on class properties or methods or inputs to the class properties or methods. And the class data itself, the attributes or properties, can be displayed in lists, dictionaries, whatever, depending on what is available from the class as a method. And you can always write one. So let's say you're working with a class that doesn't have a good method to print out its attributes. Well, you can just not override the class, I should say, but extend the class to a new class, add a method in, and then use the new class in your code.